All right, welcome back. So far we've been looking at sinusoids and the complex exponential, which is a sinusoid, but we've only been looking at continuous time. So we've gone through periodicity and the fundamental period, and the fundamental frequency, and we've done that for continuous time. Now we're going to start to look at discrete time, and there are two actually subtle differences between discrete time and continuous time, so we need to be aware of those, and let's check it out now. All right, so first of all, let's start with what is the same, and you can still apply Euler's relation. So we can still say that e to the j omega n is cosine of omega n plus j sine of omega n. This still applies. And we can write cosine of omega n as 1 over 2 e to the j omega n plus 1 over 2 e to the minus j omega n. And we can write sine of omega n is 1 over j2 e to the j omega n minus 1 over j2 e to the minus j omega n. So these things we saw for continuous time. The only difference was, of course, n was replaced by t. And so those equations, Euler's equations, hold for continuous time and discrete time. Okay, so you can always use those. Those are home base. That's our home base, or those are the money. We can always use those. Now, what is different? Well, why does just changing the letter T to the letter N, if that's what you're thinking about, how does that have any difference, or what difference does that make when we talk about periodicity? So that's what we're going to show right now. Now, and I'm going to write it out in English just to make the point more clear. We're going to say in discrete time, frequencies differing by a multiple of 2 pi are identical. And that should be, well, that's not obvious. That should be surprising to you. Frequencies differing by a multiple of 2 pi are identical. So let me give you first a continuous time example. Cosine of, let's say, pi over 4t, and we'll call it x2, cosine of 9 pi over 4t. Now, in continuous time, these are not identical. So you can plot these on your calculator or MatLab or whatever it is you use to make plots. And you'll see those are definitely not identical. And not only are they not identical, we would say that this guy is the higher frequency. Right? It's the higher frequency of the two. So it goes up and down faster than x1 of t. It has the higher frequency because 9 pi over 4 is a larger number than pi over 4. What I'm saying to you here now is that x1 of n, let's say cosine of pi over 4n, and x2 of n, we'll say cosine of 9 pi over 4n, are exactly the same signal. Those are the same signal, and because their frequencies differ by a multiple of 2 pi, the multiple is 1, right? They differ by 2 pi. This frequency and this frequency are the same, and the signals themselves are the same. So you can plot these, and if you plot, if you make a stem plot you'll see that those two are in fact identical. So why is that? Why is that the case for discrete time and not continuous time? Well, let's look at the complex exponential. Okay? And the reason I'm looking at a complex exponential is because it's mathematically easier to manipulate a complex exponential than a sine or cosine. We don't need any trig identities or anything. We just need the properties of exponents, which are very nice. And we know that the complex exponential is related to sines and cosines. So this thing, okay, e to the j omega 0 n, the claim is that if I add a multiple, so k is going to represent that multiple of 2 pi, so k is an integer. I add a multiple of 2 pi to the frequency, omega 0, that I haven't changed the signal at all, hence the equal sign there. Take a signal, add a multiple of 2 pi to its frequency, and you have the same signal. That's the claim. Okay, so why is that? Well, if I use a property of exponents, we can write this as e to the j omega 0 n, like this, times e to the j k 2 pi n. So I compare the far left of the equation to the far right of the equation, and I see, okay, I have this term hanging around, so if these two things are going to be equal, the left and the right are going to be equal, this thing here has to equal 1, right? If that thing is 1, then the claim is true. So why is that thing equal to 1? E to the j k 2 pi n. Why is that equal to 1? Well, let's take what we know about complex numbers. We've got the complex plane. This is the imaginary axis. This is the real axis. We know that this has a magnitude. This is in polar form. This has a magnitude of 1 and a phase. So this is r equals 1 and a phase of k 2 pi n. Okay, so what does a complex number with a magnitude of 1 and a phase of k 2 pi n look like? Well, a magnitude of 1 means it's on the unit circle. And then what's this angle is k 2 pi n. Well, 2 pi is around the circle, once around the circle. K is an integer, right? It's the multiple of 2 pi. So k is an integer, n is an integer, because we're in discrete time. So this is saying a multiple of 2 pi. So you can go around the circle once and you're here. You can go around the circle twice and you're still here. Circle 3 times, or negative once or negative twice, right? And you're still here. So whatever value of k and whatever value of n puts you right here. So what's the coordinates of that point? 1, 0. A real part of 1, an imaginary part of 0, i.e. 1. Therefore, the proof is concluded that frequencies differing by a multiple of 2 pi are the same. So why don't we have that in continuous time? Well, in continuous time, if you tried to prove this, you'd get something like this. You know, the n here would be replaced by a t. But in continuous time, there's no constraint that says t must be an integer. So therefore, this angle k is an integer. K2 pi then is an integer of 2 pi. But t is not an integer necessarily. So we can be anywhere in this circle, not necessarily at 1, 0. So in continuous time, this is not true. So you need to be comfortable with this, and especially moving forward in our class, that pi over 4, for example, and 9 pi over 4 are the same frequency. And 17 pi over 4 is the same frequency. and so on. So that's one subtle difference, subtle but important difference in discrete time. And let me show you a second difference, and that is, I'm just going to write it out again, not all sines and cosines are periodic. That should come as a surprise to you, that the sines and cosines are not necessarily periodic. This goes against what you've been learning in your high school math and maybe in your college math classes. You know, you've been raised in school to say, oh yes, the sine goes on forever and it's periodic. Oh, the cosine goes on forever and it's periodic. No, now what I'm telling you is that that's not necessarily true if you're restricted to only looking at integer values of the independent variable, i.e. discrete time. So let us look at why that is, again, going towards the complex exponential. And of course, e to the j omega 0, that's related to sines and cosines, so we're just going to look at e to the j omega 0. So, to be periodic, I'm going to put a question mark here, because we don't know if this is true. To be periodic, recall, I need to be able to find a capital N to add to my independent variable, that is to shift the signal by N, and I get back the original signal, okay, hence the equal sign. So if I can find a capital N such that this is true, then the signal is periodic. But remember, in discrete time, N must be an integer. Capital N this time. It has to be an integer because it makes no sense in discrete time to shift a signal by a non-integer value. I can only shift a discrete time signal by 0, 1, 2, -1, -2, and so on. I cannot shift a signal by 1.5 or pi or anything like that. Okay, so now let's take a look at the right-hand side. Use a property of exponents to make this like this. All right, now I compare the left, and remember this is still a question mark. We're not sure if those things are equal. I compare the left with the right, and I see it. I have the right here. So that means in order to make this thing equal, I need, again, this thing to be equal to 1. Okay, let me write that over here. I need e to the j omega 0 times some capital N, some integer, equal to 1. All right, let me again look to the complex plane. And I note that this complex number, e to the j omega 0 capital N, has a magnitude of 1 and a phase of omega 0 n. Okay, so I need this thing to be 1 for the signal to be periodic. All right, well, magnitude of 1 is good. That means it lies on the unit circle. But I need this complex number to be right here, because this is the coordinates of 1, 0, i.e. 1. So I need the angle to be, omega 0 n, I need it to be some multiple k is an integer, of 2 pi. If omega 0 capital N is some multiple of 2 pi, then this thing is equal to 1, and my signal is periodic. So omega 0 would need to be k 2 pi over n. So that means the original signal is only periodic if I can find an integer k and an integer n such that k 2 pi over n is equal to whatever value is here, this omega 0. Right? Let me give you a quick example. E to the j pi n. We want to know, is that periodic? Okay? Well, I identify right away that omega 0 is equal to pi. All right, so are there integers, box this equation, are there integers k and n such that k 2 pi over n is equal to pi? Yes. Yes, there are integers. So I can choose k equals 1 and n equals 2. And then I have it. Right? And so this means that the period is 2. This is the fundamental period is 2. And the fundamental frequency is pi. I could also choose k equals 2 and n equals 4. However, and this would be satisfied, yes, but however, the period now is 4, and that's not the fundamental period. Remember, the fundamental period is the smallest value of n, the smallest value for which I can shift and get back the original signal. So really what I need is the smallest value of k as well in this boxed equation. Okay, so this means that something like cosine, because of Euler's relationship, cosine of pi n is also periodic. It has a frequency of pi. A sine of pi n is also periodic. Now let's look at something a little bit more interesting. How about e to the j 2n? And we're going to ask again, is this periodic? Okay, well, can I choose integers k and n to give me 2 this time? Because I look at the constant that's multiplying j and n. The constant is omega 0. That's 2 in this case. So the boxed equation that I've got here says, okay, k 2 pi over n has to equal 2. So are there integers k and n that will satisfy this? No, because of the pi, actually. Pi is irrational, and it's definitely not an integer. So how am I going to get rid of that pi with choices of integers k and n? I'm not going to be able to. So there is no choice for k and n, and so we deduce that no, this is not periodic. And similarly, cosine of 2n is not periodic. Sine of 2n is not periodic. And you can actually go ahead and plot these in your favorite plotting software, Python, MatLab, whatever you do. Make a stem plot, and you'll see that it does not repeat ever. Okay, so we've seen some important differences between discrete time and continuous time sinusoids. We're going to rely on these differences for much of the entire course. So it's important that we get a good handle, again, on these. And if you're still uncertain about these two properties, the periodicity and the differing by 2 pi, then you'll definitely want to check out the examples video. I'm just going to run through a bunch of examples to show you if discrete time sinusoids are periodic or not. And if they're periodic, we'll find the period and the fundamental frequency.